Hello, let's continue with section 1.3, Rates of Change and Behavior of Graphs. Rate of change. A rate of change describes how an output quantity changes relative to the change in the input quantity. The units on the rate of change are output units per input units. The average rate of change between two input values in the total change of the function values, output values, divided by the change in the input values. So we have this formula. And really, don't let it intimidate you. It's pretty much your slope, right? Where f of x2 and y is your y2, and f of x1 is your y1. So y2 minus y1 over x2 minus x1. All right, given the function gt shown, find the average rate of change in the interval from -1 to 2. So I have -1 and 2. -1 and 2. Let's see what part of our graph that is. So at -1, I have 4. And at 2, I have 1. Right? That's where our graph meets that x point. So we now have our points to answer the question. We have -1, 4 and 2, 1. Now, if we wish to use our formula that we have right above, our x would be our x1, and our answer for that first one would be f of x1. For that second one, we would have x2, meaning 0.2, and the matching y would be f of x2. Now that we have each piece, we can go ahead and plug it into our function. So that we have f of x2, well, that's just 1. So I have 1 minus f of x1. What is f of x1? That's 4, right? So we have 4 divided by x2. x2 is 2 minus x1, -1. So we get -3 divided by 3. We get -1. That is our answer. We have now done a rate of change, an average rate of change. Example 2. Same idea. We're given the x's, so now we need to find the output. We need to find f of 2, and we need to find f of 4. If we plug in 2, we get 2 squared minus 1/2. That gives us 4 minus 1/2. Let's get a common denominator. 8 over 2 minus 1 over 2, we get 7 over 2. So our answer is 2, 7 over 2. That's our point. For f of 4, let's plug in a 4. We have 4 squared minus 1/4, which gives us 16 minus 1/4. Let's get a common denominator. 16 times 4 is 62. So we get 64 divided by 4 minus 1/4. We get 63 over 4. So our point would be 4 and 63 over 4. So now we have the necessary pieces to use our formula. F of x2 minus f of x1 over x2 minus x1. Okay, by doing so, we get f of x2 is 63.4 divided by 4. F of x1 is 7 over 2 minus x2, which is 4, minus x1, 2. And we would get, well, we first need to get a common denominator. So multiply top and bottom by 2, and we get 14 over 4. So 63 minus 14, we get 49 over 4 divided by 2. All right, let's write it horizontally. The complex fractions are sometimes harder to take in. So we have 49 over 4 divided by 2. Okay, that makes more sense. Remember, when we're dividing fractions, keep your first fraction, change it to multiplication, and then flip your second fraction. So this gives us 49 over 4 times 1 over 2. We don't have any common numbers to simplify by, so we get 49 over 8 as our answer. And that's it. It's just your slope. Using a graph to determine where a function is increasing, decreasing, or constant. That should have been a heading, so that should have been in blue letters. We say that a function is increasing on an interval if the function values increase as unit values increase. Similarly, a function is decreasing on interval function values decrease as the input values increase over that interval. So in general, if you're looking at a picture, you can see where it's increasing if from left to right, it's going up. So here we see that the function is increasing because we see it's going up from left to right. Same thing here. It's going up from left to right. The middle one, it's going down from left to right. Or think of slopes. It has a negative slope. And there we go. Now, this wording from A to B in the bottom, this is where it comes from. So let's take a look at increasing. Say we have a general graph, and say we have a letter, number A and a number B. But we're going to use letters to represent any number. Well, let's say A is 1 and B is 5. It doesn't matter what those numbers are, but we see that A is always going to be smaller than B, or B is always going to be bigger than A. If it's increasing, we can form a relationship for the y, since we have an f of b and an f of a. If it's decreasing, same idea, a and b, where a is always smaller or b is always bigger, however you want to say it. If it's decreasing, it has a relationship where that f of a is bigger than whatever the f of b was, since it's going down. And this is where this argument comes from. Because yes, B is always going to be bigger than A because we're looking at a comparison of the y's. While some functions are increasing or decreasing over their entire domain, others are not. A value of an input where a function changes from increasing to decreasing is called a local maximum. So let's take a look at your picture. You see how it goes from increasing to decreasing? This change happens to create a high peak. And what your next statement goes on to say is if I go from something that is decreasing to something that is increasing, it's going to give you what's called a local minimum. And while in words, it might seem so overwhelming and so confusing, if you look at your picture, it makes sense that that's a low peak, that's a high peak, that's a local minimum, it's a local maximum. We can also have a collection of highs and lows. If it's the highest of the high points or the lowest of the low points, then it has a special name. Local minima and local maxima. A function f is an increasing function on an open interval if f of b is greater than f of a for every two input values, a and b, in the interval where b is greater than a. A function f is decreasing on open interval if f of b is less than f of a for every two input values a and b where the interval b is greater than a. So that's talking about my two pictures that I kind of drew for you here. It's talking about when it's increasing and when it's decreasing. Notice A and B is just talking about a smaller and a bigger number, but that Y is going to be a higher value or a lower value in your X and Y's. Lastly, a function f has a local maximum at a point B in an open interval AC if f of b is greater than f of x for every point x in the interval. F has a local maximum at a point B if the interval f of c if f of b is less than f of x for every point. So let's take a look at this example. Given the function p of t in the figure, identify the intervals in which the function appears to be increasing. All right, remember, we read our graphs the same way we read our English. We read it from left to right. Okay, so we want to find out where it's increasing. So where is it going up from left to right? We see it's going up from 1 all the way to 3. And it keeps going up again from 4 all the way on to infinity. So let's describe these points. These match up to the 1, and this matches up to the 3. This matches to the 4, and it goes on to infinity. So they are increasing from 1 to 3, and again from 4 to infinity. These are the values from which they're increasing. Remember, it always attaches to your x values because that describes our function. Those are the values for which our graph is increasing. All right, that's it for this section. And next we have problems numbers 5 through 41, every other odd, in your OpenStax textbook. That's it for this section. Thank you.